Thank you very much. Yes, so as the title shows, I will be guiding you into how type 2 supernovae work without the use of distance ladder, and I will just also make some detours into the other techniques that Frederick did not mention in his talk. So we have had very nice overviews about the distance ladder, especially the switch between the first and second rung from both Teresa, Abi, and Xiang yesterday. But if you take a look at the plot in the CosmoVerse paper, you can notice it very nicely that there's actually a whole plethora of different techniques, and there are a couple of them that are actually mentioning that there are no rungs involved in the estimation, such as, for example, the masers that I'll be talking about, and Frederick's lenses, and also type 2 supernovae as well. And the idea of this talk is to just try to introduce the remaining techniques in this aspect as well. So in this overview, with my and Frederick's talk combined, we will basically learn about these methods. So there is one method that Frederick already mentioned, was lensing, of course, where we can use both quasars and supernovae as the variable source behind the lenses. I will not touch upon these. However, we also have techniques that involve interferometry, such as masers and the ones that use supernovae as well. And the one that I will be talking about the most is the modeling, the direct radiative transfer modeling of type 2 supernovae, which also allow for the estimation of physical parameters and hence the distance as well. So to start with, I would like to start with masers. So megamasers are essentially coherent microwave radiation sources that come from excited water in the accretion disk of active galactic nuclei, AGN. And these are very nice because they trace the accretion disks on subparsec scales. What happens here is that here you have a sketch from Violet Implezieri of NGC 4258, which is the most well-known maser that is used for distance estimation purposes. Here, at the maser positions, the supermassive black hole is dominating the gravitational potential. So basically what you have is a Keplerian orbit around the supermassive black hole. And what's really great about this is that if you know this setup, that you have a Keplerian orbit, you can measure distances to the masers very easily. This is a plot that I got from, this is a slide that I got from Frederick. So here what happens is that you have your maser system. You have the high velocity, the red high velocity masers that are coming towards you and going away from you, these ones basically on the side. And you have the systemic masers, systemic velocity masers, that are basically not moving either towards you or away from you, they are moving in parallel with us. And you can basically measure the angular distance between the center and the maser sources that are moving away from us using interferometry. For this VLBI, interferometry has been used for long. And basically with this you can also set their velocity, whereas with spectroscopic follow-up of the systemic velocity masers, you can get the centripetal acceleration of the masers, which allows you to break the degeneracy between the mass and the distance in the Keplerian orbits, which also then yields a distance to the maser sources in the end. So masers have been known for long, and there have been systematic searches for them for quite a long time. Today, according to Dominique Pesquet's overview in the CosmoVerse paper, we know about 30 confirmed cases, confirmed masers. Out of these, there are 6 that are more or less clean objects, basically. This was overviewed by him in the Cosmic Megamaser project, which was published in 2020. Here you can see the Hubble diagram of these masers, and here you can see the individual age-naught posteriors that you can get if you measure the distance to each of these maser hosts. If you combine these together, you get a Hubble constant of about 74 kilometers per second over megaparsec with relatively big error bars, but this is completely independent of the distance ladder, and that is the important bit. The main limiting factor today is the VLBI observations. So with more observations, we could actually go down to higher precision. And they note that with the start of the next generation very large array, a much bigger volume will be probed in the future, and this will allow us to actually increase the maser sample quite substantially and go down to much higher accuracies. So they say that with the start of NGVLA, we will be able to go down to percent level precision independently of the distance ladder. The other technique that I want to mention before I go on to the modeling of type 2 supernovae is intensity interferometry of supernovae. This is something that actually was published on arXiv not so long ago, so I didn't really have the time to delve into it. But the basic idea is that you have the ejecta that is expanding after the explosion of the supernova, and you basically just try to use optical interferometry to probe some lines in the spectrum of the supernova to basically measure how it's expanding. What you're trying to measure is the change of size from the intensity function, and you will compare this to the ejecta expansion velocity that you're measuring from the spectra. They say that they need an array of about 20 kilometers to go down to 10% precision, and for this they used an optical line, so this would be an optical interferometry, and this would be able to probe the very near universe between 3 and 12 megaparsecs. So basically that is where the first rung of the distance ladder operates, where Cepheids and TRGB is operating today mainly. These are very expensive observations, and parameterization in high velocities and velocity estimations might have some shortcomings as well, but this is also some avenue that might work in the future. Okay, but now I would like to move on to how do we measure H0 from the modeling of type 2 supernovae, and this is what I've been working on with our group in Garching. Here you can see a photo of our group with some photoshopping included. So the core group involves Bruno and Wolfgang, who are the PIs of the group. There you have Christian and Stefan, who have been the main workers of this group, who have been devising the whole pipeline that I will be introducing. We have Sherry Suyu, who is our blinding expert. We have myself, and we have a couple of master students and bachelor students who have been joining us over the years and been contributing to the project, such as Sabrina and Gabi and Alexander. And we have Stefan and Jason, who have also been working a lot mainly on the reduction of the data. So in this work, we are using type 2 supernovae, and just to give you an idea, what are these? So mostly when you're looking at cosmological papers, the supernova type that comes across is type 1a supernova, which is some explosion of white dwarf stars in probably a binary or trinary system. However, what we're using are type 2 supernovae, which are the explosions of red supergiant stars. And contrary to type 1a supernovae, here we exactly know what's going on at the explosion. What we know is that what happens is basically we see the final gravitational collapse of an old red supergiant star and the subsequent repulse from the forming neutron star in the core. We have been observing progenitors of type 2 supernovae as well. We have been seeing them with HST photometry. And what is also great about them is they are actually more frequent than type 1a supernovae in a volume-limited sample. So if you take a volume-limited sample, more than half of the supernovae will be type 2 supernovae. We are only seeing more type 1a's because they are inherently brighter. So if you go farther away, you will eventually get more of them than type 2's. These are also very bright, which allows us to observe them out to a redshift of 0.4. So we can actually use them as cosmological probes very effectively. So to give you a basic idea, this is a schematic picture of what happens in a type 2 supernova when it explodes. You have the core, which is where you have basically the neutron star forming in the middle. This is where basically the shock is being deposited into the ejecta, which is pushing the material outside. You have a sharply defined region in this schematic picture within the ejecta of the hydrogen envelope of the supernova, which is called the photosphere. This is basically where the optical depth of the ejecta drops enough that you can finally see the photons that are inside the ejecta. They finally escape, and you can get them basically. This is what essentially, this is in some approximations, this is what sets you the spectrum of the supernova essentially. What we are trying to do in our method is basically we are trying to track how this photosphere evolves in time, how it changes its temperature and its size. And this method, because of this, has been called the expanding photosphere method. What we are ideally trying to determine when we are using the EPM method, the expanding photosphere method, is how big this photosphere is at given epochs and how hot it is. Because if you have these two measures, you can directly estimate the luminosity based on the Stefan Boltzmann law. And this is not new. I mean, this has been around for about 100 years. This is all based on the Baade vesseling technique that was originally developed for Cepheid stars, and then was introduced for supernovae as well. The first use of this method for Hubble constant estimation is also not new. I mean, this was done basically 50 years ago for a Type 1a supernova, which is a bit different. We learned about this since then, but this has been around for quite a while. This is what set the basis for our technique. So to measure how hot the supernova is, of course, we have to take a spectrum. Here is an example from an optical spectrum for Type 2 supernova. With the black one, you can see a black body and with some line features of hydrogen, helium, again hydrogen overlaid on top of it. These are the so-called P-Cygni features. And they allow you to measure velocities of the ejecta, basically, because they are directly connected to outflows happening at an object. So by measuring these P-Cygni lines and modeling them, you can get an idea of how big the supernova is. And by putting a black body on top of the spectrum, you can actually measure how hot the supernova is. Of course, reality is not that simple, so this has been how people have been using this method in the past decades. But there are various shortcomings when we are trying to use this method, because of course the spectrum is not a black body. We have features, and we have this so-called continuum dilution, which comes to the fact that the spectrum itself is not thermalized effectively. There are other sort of scatterings than what a black body would assume, other sort of optical opacity than what the black body would assume. Also, what is also complicating the issue is that lines are not probably in the photosphere. So if you are making these assumptions, you will be biasing yourself inherently. And this has been something that has been causing the method to be influenced significantly by systematic effects. And this is why it has been not used that widely for measuring H0 over the past decades. However, physics did not stop. And people have been working very tirelessly in the past 30 years to come up with an effective way of modeling properly these Type 2 supernovae. And what we are doing today is that instead of making these two assumptions and just measuring lines separately, putting black bodies on top of the spectra separately, we are now doing complete radiative transfer modeling of the entire spectra, where you have all the parameters together in a correlated fashion. So in here, the physical parameters are controlled by the supernova model that you are devising based on radiative transfer principles. And then we compare these models directly to the observed spectra. And here we will have no problems with the flux dilution that I've mentioned, because the radiative transfer model will know about it. It will handle it separately. What we have been using for this purpose is a TARDIS code, which have been developed originally for Type 1a supernovae, but has been adopted for Type 2 supernovae by my supervisor, Christian Vogel. The problem is that even with making these models very effective, it still involves a lot of time to try to fit these to actual observations. Modeling one spectrum, carrying out one radiative transfer model can take days. And if you want to model an entire spectral time series of a supernova, it will take months. And this is what has been the bottleneck for measuring H0 over the past decades using this technique. However, my supervisor Christian Vogel came up with the idea of, instead of trying to simulate every single time you have a new spectrum that you want to model, you can try to emulate. So instead of just trying to rerun your radiative transfer model for every single spectrum, you can just basically train an emulator by setting up a grid of spectroscopic observations, and with some clever fitting technique, you can basically interpolate between these simulations, radiative transfer simulations, and get a fit of an observed spectrum way faster than previously. This basically allows us to do an actual chi-squared based fitting of the observed spectra, which then yields us very precise and reproducible physical parameter estimates for each of the individual spectral epochs. All right, and now that I said the method, I would like to go through a few of these checks that we've been working on to trying to validate this method, basically. So the first check is a check of internal consistency. Because of course, now that we have this method of modeling Type 2 supernova spectra, we want to see whether it's not only just precise, but it's also at least internally consistent as well. By internal consistency, I mean what happens if you just fiddle around a bit with the physical parameters of your supernova. If you switch out your supernova in the galaxy, would you still get the same distance? Would you still get the same parameters in the end? Or would you just be completely off the grid after you made some changes? So of course, because this means that if this happens, then we will have to adjust our parameter precisions that we claim at the end. And one very easy way to test this is through supernova siblings. So supernova siblings are supernovae that occur in the very same host galaxy. And the great thing about them is whatever you do about them, you know that they are in the same galaxy. So in the end, you should have the same distance for the supernovae. So if you perform the radiative transfer modeling for both of these supernovae, you should, at least in principle, get distances that are in agreement with each other. We performed this test using a literature sample from 4 host galaxies. You can see here an image of the 4 host galaxies with 2 of the supernovae in each of them. These are all nearby host galaxies. This is not a cosmological sample. They are all very, very nearby to us, somewhere within 20 megaparsecs. Here you can see the modeled spectral time series for each of the 4 host galaxies. So each panel corresponds to one host galaxy with the supernova pairs. I can zoom into one of them. Here you can see basically that each of the spectra within the time frame that we modeled them are fitted very nicely by our radiative transfer model. And then we can convert these to distances. Here you can see the individual distance posteriors that we got for each of the 2 supernovae in each of the 4 host galaxies. And what you can see here is that they match quite nicely within the claimed uncertainties. Of course, I mean, please note that on the x-axis, each of the panel is different because we're talking about different host galaxies. So they are all matching up nicely, at least in the first order, within uncertainties. But of course, to track whether we are influenced by any systematics, 4 objects, 4 pairs are not enough yet. So what we are working on right now is we are trying to extend this sample. We're trying to look for more comparisons like this. For this second sample, we of course have the literature sample that we've been working with, but we had our own telescope time on VLT, and we have been taking a deeper literature dive this time. And now we have a much wider sample of sibling supernovae, where we can do the analysis both on the member objects, and we can try to compare the distances, actually quite high precision. I did a check, and basically to half of these new host galaxies, we can do distance estimation better than 10% for each of the supernovae that are in the galaxy, which will allow us to do a very precise comparison between the distances. This is some work in progress, basically. So there are 2 philosophies that we can make use of when we are trying to compare distances for the sibling supernovae. One of them is that we can check how robust is the method. That was what we did in the literature analysis paper. Here we basically just infer a distance to each of the supernovae in the host galaxy, and we just compare them, easy as that. But we can also try to use this method, because all of the supernovae are independent measures of the same distance, basically. We can combine them to get a high precision distance at the very end, basically. So we can say that we can combine essentially the distance measures of the supernovae to get a final combined posterior for the host galaxy distance, which would allow us to get very high precision anchors for other methods, for example. So for this example, we can go down to 3% precision by combining the data from all 3 supernovae in this one very host galaxy. We can also do other comparisons, because of course we don't only have type 2 supernova siblings, but we can also compare ourselves to the distance ladder just to test it. Because what we can also find is siblings of type 1a and type 2 supernova siblings. Here I show some examples of the recently found objects that are already somewhere in the Hubble flow. So not only we can basically check how consistent is the estimation of type 2 supernova distances, but we can also cross-check how well do type 2 supernovae do compared to the distance ladder technique. All right, and now that we are talking about direct cross-checks, we can not only compare supernovae to supernovae, but we can also do a cross-check between supernova and independent distances. This is a work that we have been doing with Richard 2 years ago, where we compared distances from the distance from a type 2 supernova with the Cepheid distance of this very nice host galaxy M51. And we also had some literature estimates from TRGB for this host galaxy that we could use as a baseline for our comparisons. So what we did is that we estimated the Cepheid and the supernova distance for this host galaxy, and here is the result. Basically, I'm showing here the distance posteriors that we got from different techniques. The red one is a Cepheid, the blue one is the type 2 supernova distance that is completely independent of everything else. We also have the planetary nebula luminosity function and the surface brightness fluctuation distances for the same galaxy as well. And here you have the TRGB. So here we had some offset between the TRGB and the other techniques, but the reason is likely due to the TRGB field being not well placed for this analysis. So here we have a good guess of what caused this offset. We were a bit constrained on time on my side, so we didn't redo the TRGB analysis based using a new field, but I think this is something that we could actually do, and we could try to get a much higher precision comparison between these distance estimations. Of course, you could ask, is M51 the only object where you can do such distance comparison? And the answer is no. But since nobody has been following up type 2 supernova host galaxies with HST observations, the comparisons are less precise. So the currently available host galaxies where you can do this comparison has various different shortcomings. And I don't really want to delve into the details, but currently we only have one host galaxy where we can do this comparison between various distance estimation techniques very precisely. So we really need to expand this sample. And in this sense, I wanted to mention briefly the ESO workshop that we had one month ago, actually, that C. Young also mentioned yesterday, where we are trying to come up with a consensus of the use of different ways to measure H0 using various different stellar indicators. We are trying to collect all the data, decorrelate them, and just try to measure H0 along well-defined basic principles. And I just wanted to show here a plot that Richard made for this purpose, which is a very nice metro line of the different techniques. I don't really want to delve into details, but every single line corresponds to one path that you can take to H0, and here is what type 2 supernovae do currently with this modeling technique. But as I showed with this cross-check, we can actually try to connect these type 2 supernovae into many other different pathways as well to get a comparison between the different techniques. All right, and for the last 5 minutes, I want to talk about how we can estimate an H0 and what is the current stance. So my supervisor did a literature dive to try to estimate H0 solely based on data that has been already available. He found 10 supernovae in the literature that were situated in the Hubble flow, had good enough constraints on when it exploded, and had good enough data for the modeling. And he performed a spectral fitting for each of these supernovae. And this is the final Hubble diagram that you can get based on type 2 supernova modeling alone for this literature sample, along with the best fit for this best fit Hubble law. We can also try to combine the individual models separately instead of basically just constructing a Hubble diagram based on a supernova to supernova basis. Basically, we can use every single spectra and put them on the Hubble diagram separately. This is something that I can talk about if you're interested later on in the discussion session. But basically, this allows us to have a more precise H0 estimate by decorrelating the individual spectral models. So you can kind of move away from the single supernova Hubble constant estimation and just try to do it on the basis of measuring spectral parameters. The final distance that we got from this Hubble constant estimation is about 75 plus minus 2 kilometers per second over megaparsec. This work has been accepted in ANA just 2 days ago, so it's out finally. So this is the very first type 2 supernova Hubble constant estimate that we have with this new technique, with the radiative transfer modeling. But this at the moment does not include systematic errors. We are trying to work on it to try to estimate how much we're influenced by certain analysis choices and certain underlying problems. Also, at the very end, so this was based on literature data, but we are also trying to run for a more precise analysis by a dedicated data set. And for this, we had a VLT large program that was running for 3 years on ESO VLT UT1. And we observed 26 Type 2 supernovae in the Hubble flow. This collaboration was named ad hoc. So this is where the collaboration name comes from. That stands for accurate determination of age not from core collapse supernovae. So we collected a very nice, very nicely detailed spectral time series for each of these supernovae. Here you can see the distribution of our object on the sky with the redshift distribution that we obtained. And the goal is that we are basically trying to model each of these supernovae separately and then try to get the necessary physical parameters that we can put on the Hubble diagram, the modified Hubble diagram in the end. What our advantage is that we are not constrained by the stellar background or crowding. This is something we can control and reconstruct and measure. We can also measure our reddening separately based on the spectral modeling. So this is not determined based on a statistical approach. And we can also obtain sub 10% distances for each of our supernovae, which allows us to get a very high precision measurement. And this is where we are standing right now. So we already have a blinded Hubble diagram. We are having some new versions of the analysis running in the background. At the moment, we are somewhere on statistical precision of 2%. I'm not giving exact numbers because I don't want to look at the exact numbers. But we are basically running the analysis one last time, and the unblinding will happen sometime around June, when we'll have a final Hubble constant estimate based on the ad hoc sample as well. All right, and I think I went over time a bit, so thank you very much for your attention, and I'm happy to take your questions.
Thanks, Geza, for the wonderful talk. I would like to know a little bit more about how uncertainties are treated in this emulator approach. Can you tell a bit more about that aspect of it?
Yes. It's a bit difficult, right? Because when you're fitting spectra, it's a bit hard to put uncertainty estimates on the physical parameters that you can get. What we are propagating right now is an uncertainty in the reddening, in the flux calibration, in the photometry, which basically gives us a sample or a range of spectra that we can actually fit, and from that we can get basically a posterior for each of our physical parameters. What essentially happens is, maybe I have a plot where I can show this. Yeah, something like, something like this basically. That we have some errors, of course, in the photometry, which gives us some errors on the flux calibration. What is the tilt? What is the exact tilt of the spectrum? And we can basically try to fit a range of spectra because of this. And from that we will get essentially a range of best fitting spectra that match our distribution set by the uncertainties in the photometry and the flux calibration. And that we propagate into our analysis to the very end. We have other uncertainties, of course, coming from the peculiar motion that we are treating. What we cannot treat at the moment is what are the uncertainties that are coming directly by the choice of the radiative transfer code itself, of course. I mean, that's something that will require some more analysis.
Yeah, the other question is, if you're doing comparisons between the sibling supernovae or also between supernovae type 2 and type 1, is there a way to get rid of the shared error in the methodology so that you're really, in those cases, can benefit not just from the full distance error, but from relative precision?
By shared distance error, you mean? Can you please?
So if you have two distance for the same galaxy from these twin supernovae, and there's some element of that which is just shared between those two galaxies, and other things are different. So presumably, if you could somehow take out that joint systematic, you would get an even tighter comparison statistically.
We did not really think about that. I mean, we did not go down that rabbit hole yet. I think we could try taking a look into what happens there. I mean, right now we are really just not even caring about what is the exact distance that we are getting in the very end. So that avenue that I mentioned, that we are combining different distances together and we are trying to just reduce the uncertainties and maybe even compare different type of objects. That's a new avenue. We haven't gone down that path yet. What we are trying right now is really just whatever the distance is, we don't really care. Let's see how much we are in agreement at the moment. Because we are now more concerned about the systematics that can happen to supernova. So we are not doing anything further than that at the moment, but we will.
First of all, congratulations on pushing this method forward. That's very, very nice. I have a question about exactly this slide. So it's good that, no, the one you just had.
Okay, sorry.
Which is exactly because you passed very quickly the subject of extinction, which is critical for these things, and focusing what you have written here. You say pick the best fitting EBV, but of course that's completely degenerate with the RV, right? That's a completely degenerate with this extinction law. So how you guys, what are you assuming for extinction law here?
Extinction. I mean, we are in optical, usually in low extinction areas. So the extinction law itself doesn't have it's not a major source of its systematics. The RV itself is, because we have to pin it to some value if you want to run the analysis. Right now it's pinned to 3.1.
Which is not what we find.
Which is not what we find. Yes. I mean, of course, we have multiple problems here because this is informed based on the galactic extinction, but we of course can have host reddening as well, so which is sourced.
Right. I'm thinking about the host reddening, not too much of the Milky Way. Yeah, I'm just thinking of host reddening. Yeah. So I would be curious to know if when you do these systematic tests, when you will be testing a range of RVs.
Yes, okay. Yes, that's something, but that's something that is done separately to put an error bar on it. Basically, this is not part of the emulator, so we are not marginalizing over the RV parameter. We are just tuning it at the very end and trying to put a number of what is the final error. This is still work in progress as well.
So I just wanted to ask, how far out do you think the expanding photosphere method can be pushed? In terms of sort of calibrating supernova host galaxies, for example?
So right now, the sample that we have is limited at a redshift of 0.08. We have one object at 0.18, but that was a lucky find. We are limited at the moment by the feeder surveys, such as ZTF or Atlas, that are discovering these objects early on. We need very well-constrained time of explosions for the method, because time of explosion is one of the fit parameters, which is, if it's constrained separately, that increases our precision quite substantially. And this is the major bottleneck right now, because these feeder surveys at the moment only find supernovae reliably until 0.1 redshift. And then we have to make our quality cuts, that we have to be certain that we found a type of supernova, because spectroscopic follow-up is very expensive.
But like in the LSST era, how far do you think it could be pushed, like in say, 5 years?
It really depends on what the LSST data will actually be and how we can find the supernovae in them, and whether it's good enough to constrain time of explosions. I would say that we will be able to push it out to a redshift of 0.2 for sure, maybe 0.3, but that's really scraping the bottom of the bucket. 0.2 for sure, because that's already something that is achievable, for example, with Pan stars. And if LSST will really go down to a magnitude of 23, that will allow us to probe that range as well. So I would say reliably 0.2, 0.3, but in principle, spectroscopically, we would be able to follow them up until 0.3 or 0.4 as well.
Thanks.
Thanks again for the speaker.